Okay, at the beginning here, we're going to have you go over a brief review of a couple terms. So atomic mass, atomic number, A number, Z number, and then to take a look at these particular isotopes and tell me how many protons and neutrons are in each one. So go ahead and pause this video and walk through that process. And then when you're done, hit play, and then we'll walk through it together. Okay, let's take a look at atomic mass. We know what that value is. That is your protons, the number of protons, plus the number of neutrons in your nucleus. Our atomic number is our number of protons, and this is unique for each element. So unique for each element. Our A number, of course, is our atomic mass. And our Z number is our atomic number. So those actually reflect back on what we just defined. So this is my atomic mass, that's my atomic number. And then to find my number of neutrons, I'm going to take that atomic mass, which is my A number, and then subtract the Z number, which is my atomic number, and that's going to give me my number of neutrons. All right, so let's go ahead and look at titanium, cerium, cesium, and radon. These, what I'm going to do is look it up on just a regular old standard periodic table of elements. And 48 is the isotope of titanium. So when I go and look at titanium on the periodic table, it has the atomic mass number of atomic number of 22. So I know that that's my number of protons. To get my number of neutrons, I'm going to take that 48 minus 22, and that's going to give me 26. So that's my number of neutrons. Go ahead and pause this right now if you have not finished the rest of them, and make sure that you can make those adjustments and get them accurate. Otherwise, we're going to keep going. So cerium 140, our number of protons is 58. If we look on the periodic table, and 140 minus 58 gives me 82. So that's my number of neutrons. Cesium, I have 55 is my atomic number, and then 133 minus 55 gives me 78. So that is my number of neutrons. And then finally, radon, I have 86 on my periodic table for radon, and 222 minus 86, it gives me the value of 136. Okay, all right. So now we have reviewed that quickly. I wanted to talk a little bit about some characteristics of radiation before we get into the different naturally occurring types of radiation. The first is the cumulative nature. So you accumulate exposure over your lifetime. So it's not like you can get it purged out of you. So whatever radiation exposure you have, it continues to build. These are measured in picocuries. So picocurie. And so that would be 1 times 10 to the negative 12 curie. So those are very, very small units of measure. The NRC is the Nuclear Regulatory Commission. And they are pretty much the person, or well, not the person, but the organization that has a say over anything that's radioactive. So if you are not messing with radioactive materials, but if you are working with radioactive materials in the lab, which we will not be, you are required to badge in. You have to keep a log. The NRC can come and examine that log at any moment. When people are wanting to enrich uranium for power production, the NRC is usually involved as well. So they're an organization that anything that touches basically radiation, they are the ones who are kind of the gurus and the standards and the people who know what's going on. Lastly, one thing that we got to take a look at is called a dosimeter. And this is a badge that measures radiation exposure. So anytime you work in a laboratory environment where you will be around radioactive materials, that could be for nuclear physics. It could be actually working with X-ray machines, or let's say you work in a vet's office as a vet tech. You'll have to have, usually they just call it a badge. And then typically that gets sent off and read and logged. The dosimeters that we had in our nuclear lab, we actually read them on the spot, wrote it down in a logbook, and then we read it after we did our experimentation. Okay, so let's look at the different types of radiation. We'll talk about the symbol, what it is, the formula that you might see in an equation, and then how we actually analyze it or get information from it. So our first one is going to be alpha, and these are all Greek symbols. So this is a lowercase alpha, and beta is this with a tail on the end. Notice too that when we talk about beta radiation, there's beta negative and there's beta positive. We'll talk about those in a minute. And then we have gamma radiation. So that gamma looks like a skinny alpha that's been rotated about 90 degrees to the left, counterclockwise. All right, so what is it? Well, an alpha particle, okay, we always talk about alpha particles. It's 2 neutrons and 2 protons. Often it's called a helium nucleus in its description, because that's exactly what it is. It's 2 protons, 2 neutrons. Beta negative is radiation emitted by an electron, from the nucleus. And we'll talk about that in a second. Like, well, wait a minute, there's no electrons in the nucleus. Yes, if we have something undergo a transformation. So we have a neutron that busts into a proton, an antineutrino, and then an electron. So that's where that comes from. Beta positive is going to be kind of similar, and it's going to be a positron from the nucleus. So it's a proton that emits a positron, a neutrino, and a neutron. So we will, again, get into the details of that and how it responds in an equation at another time. And then gamma, there's really not much to gamma. It is energy. In a reaction equation, it really doesn't play much of a role except a holding place. It is what's called a photon. So you may have it shown as a little snippet of a wave, possibly. So let's look at the formulas of them. So the formula of an alpha particle, I've seen it written 2 ways. The first way is going to be the most common, which is this 4,2He. That's your helium nucleus. Again, when we're talking about things from the perspective of physics, we really don't care about what's going on with the electrons. We're really looking at the interactions between the nuclei. You could possibly see it, although this isn't as common, as this. So an alpha with a 4,2. In beta land, our beta negative is going to be -1,0, and our beta positive is going to be +1,0. And then as far as gamma is concerned, again, you may see it as just a wave. Sometimes you'll see it in an equation like this, where you have the symbol and then you have a show of 0 change to your atomic mass and 0 change to your atomic number. All right, now that we have that, let's take a look at strength shielding. An alpha particle, I'm going to put in quotes that it's weak. And I don't mean, obviously if you ingest something or inhale something, that's going to be a lot more damaging than it coming at you from the outside of your body. So when I say weak, it can cause damage. I just don't want you to compare it to gamma and think that it's of the same strength. It is a large emission. It's the largest of all the emissions. So it's going to be shielded fairly easily. So we could say a piece of paper could easily shield that, meaning that it stops it from moving. All right, when we look at beta, whether it's beta positive or beta negative, this is a little bit stronger. It's not the strongest, but our shielding is a little bit more particular. So we can have anywhere from a sheet to several inches of aluminum is our shielding on that one. And then gamma, this one holds the most energy. So I'm going to say that this is our strongest of all of them. And it's quite frankly, if you have a high dosage of that, that's where you're getting into a lot of your genetic mutation and some horrible, horrible things that can happen. This is what requires several inches to several feet of lead in order to shield it. So lead is an extraordinarily stable isotope. So a lot of your larger isotopes will continue to decay until it gets down to lead. Well, how can you tell if there is radiation around? Really, the only way to analyze an alpha or beta pattern is to put it into an alpha-beta spectrometer. And we don't really have those handy as a normal member of society. Of course, science labs would have something like that if they're prepared to do any kind of analysis of radiation. There is one, though, for gamma called a Geiger counter. And this really just says, it kind of looks at the concentration and the presence of gamma and X-rays, because it will pick up X-rays. And so a Geiger counter will start making like a beeping or a ticking noise and make a bunch of ticking noises if you are closer to a source that's a little stronger. So if I have just some ambient radiation that might be out there, I might hear like a little tick, 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 tick on my Geiger counter. But if I have a higher concentration, it will go faster, like tick, 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 tick. So you'll see that that's kind of, it doesn't give you a whole lot of information, but it will tell you that it's present. And it will tell you where it's going to be in a higher concentration so that you can potentially find a leak. So we're going to pause the video here. We'll do another one for reading our table of nuclides.